Hello and welcome, Mr. Johnson here. And in this video, we're going to be looking at predicting products specifically of synthesis reactions. You might notice that this is a little bit different of a setup from normal. That's because the normal setup that I have isn't working quite right. So I do apologize in advance if the audio sounds a little bit weird or if there's a glare on the screen that causes some things that not be able to be seen as easily. But anyways, we're going to move on. So predicting products specifically of synthesis reactions. Now, there are numerous types of reactions. There are synthesis that we're going to look at in this video. Then there is decomposition and there's combustion, which will be a separate video. And then there is single displacement and double displacement, or single replacement and double replacement, that we're going to look at in a third video. But this video, again, is just about synthesis and the types of synthesis reactions that we can end up experiencing in chemistry. So first off, what exactly is synthesis? Well, a synthesis reaction is where you are taking two or more reactants and putting them together into a single product. So in that, what we typically see as a general reaction is this idea of A plus B, so substance A plus substance B, undergoes a chemical process to then produce compound AB. But there are a lot of different types of synthesis reactions, what all you can combine. And that's what we're going to look at in this video. So let's go on and jump into the different types. First off, there is synthesis where you're combining a metal with oxygen, and those are going to produce oxides. Then you can take metals, combine them with sulfur. Those are going to produce sulfides. You can also take group 1 or group 2 metals and combine those with halogens, or column 17, or halogen groups, and you're going to get metal halides. We can also do some more complex synthesis reactions where you take metal oxides and you combine those with oxygen, or not with oxygen, sorry, with water, produce metal hydroxides, or you can take non-metal oxides and combine those with water and get oxyacids. So we're going to go through just step by step how to predict the products for each one of these types of reactions. So let's start out with the idea of combining something with oxygen. So if I'm combining a metal with oxygen, and the other thing that I should mention is that these are all going to be ionic compounds. We're going to have a positive component and a negative component that combine to form our compound. And because they're ionic and we have to do a balance of charge, we're going to take those charges and cross down. Okay? So if you haven't watched my video on writing formulas, I highly recommend that you pause this video, go back and watch that video first. And what I'm going to do with crossing down charges will make a lot more sense. Okay. But when we look at synthesis with oxygen, I'm going to have my metal component plus O2 produces my metal oxide. So this is another way that you can see that general reaction. A plus B yields AB, where that metal can have different charges. If we look at the periodic table, column 1, that's going to be a 1 positive. Column 2 is a 2 positive. If we skip on over to column 13, we've got a positive 3. Okay, so we can have multiple charges. So this again is just a generic type of general reaction. But anytime I combine a metal with oxygen, for example, if I take magnesium, react that with oxygen to produce my metal oxide, what I have to do is always think about what would be the charges of these two components when they're in a compound. So magnesium from the periodic table, we'd find it to be a 2 positive. Oxygen from the periodic table, we'd find that as a 2 negative. And in case you're wondering why I've got this 2 on oxygen, it's because it's one of the 7 diatomic elements. Okay? And anytime we have oxygen by itself, it's always O2. But when I combine it into a compound, it is just plain O, and then I've got that charge of 2 negative. And to figure out what my product is going to be, I'm going to take the numerical value of magnesium's charge and cross it down to be a subscript on oxygen. I'm going to take the numerical value of oxygen's charge and cross that down to be the subscript on magnesium. And initially, I get Mg2O2. But this ratio of 2 magnesiums to 2 oxygens can be reduced. And as such, when I reduce each of those subscripts by the factor of 2, I get a product of MgO. That is my metal oxide. Okay? If I take another metal, for example, instead of magnesium, if I were to take, say, sodium and react that with oxygen, I'm going to do the exact same process. I'm going to think about the idea that sodium, when it's in a compound, would end up having a 1 positive charge. Oxygen within a compound, again, is going to be that 2 negative charge. And to figure out what my metal oxide is going to be, I'm going to take that numerical value of sodium's charge of 1, cross it down to become the subscript on oxygen, the numerical value of oxygen's charge 2 to become the subscript on sodium. I get Na2O, unwritten 1. And because I cannot reduce those subscripts, that becomes my formula of my metal oxide, sodium oxide. One more example for you, just so you can see of each type of charge. If I were to take something from column 13, for example, aluminum, and I combine it with oxygen, once again, I'm going to think about what charge would aluminum have within a compound. So when I look it up on the periodic table, I find that aluminum would carry a 3 positive charge. Oxygen, as always, would be that 2 negative. And again, I'm finding that 2 negative by looking at its column's charge. And then, as I've done in the previous 2 examples, I cross the numerical value of those charges over. And in this case, Al2O3, I cannot reduce those 2 subscripts. So I can write the formula of my metal oxide to be Al2O3. So aluminum oxide, my metal, and then oxygen. So that's synthesis when we combine a metal with oxygen. And this is very similar to if I were to combine a metal with sulfur. Instead of getting a metal oxide, I'm going to get a metal sulfide. Okay? So let's look at 3 examples for reacting a metal with sulfur. The first I'm going to do, we'll just start out with a positive 1 charge. So metal is sodium, combining with sulfur to get my metal sulfide. So again, just like in the examples we were looking at oxygen, we're going to think about what would these components have as charges within a compound. So sodium, when I look it up on the periodic table, I find it to be a 1 positive. When I look up sulfur on the periodic table, I find it to be a 2 negative. And as we've done in all the previous examples, take those numerical charges and cross them down to become subscripts. I get Na2S1. I cannot reduce those subscripts, so that is my formula, Na2S, unwritten 1. So sodium, my metal, reacts with sulfur to produce a metal sulfide, in this case, Na2S. If I change out that sulfur for magnesium, again, we think about it as what would be the charge of magnesium within a compound. Magnesium is a 2 positive. Sulfur on the periodic table, we still find that as a 2 negative. And then I cross down those subscripts, Mg2S2, but I can reduce those subscripts of 2 down to 1. So as a result, I get magnesium sulfide as my metal sulfide with the formula of MgS. Last example on the sulfurs. If I were to take that aluminum and react it with sulfur rather than with oxygen, exact same process that we've already done. I'm going to look up the charge of aluminum, the periodic table, which we've already established is a 3 positive. I would look up the charge of sulfur on the periodic table, which we've already established to be a 2 negative. And we're going to cross down those numerical values like we've been doing all along and get Al2S3 as my metal sulfide. So that's synthesis with oxygen or with sulfur. And what I'm hoping you notice is that we carry out the exact same process, whether it's with oxygen or with sulfur. We're finding the charge on the metal component, finding the charge on oxygen or sulfur, which in both cases are a 2 negative, and we're crossing down those charges to get our subscripts on our product formula. So that is synthesis with oxygen or with sulfur. So now let's look at those group 1 metals and group 2 metals with halogens. So if I'm looking at a group 1 metal, so my group 1 metals, if I spell that correctly, getting ahead of myself, group 1 metals all have a charge of 1 positive. My halogens, column 17, all have a charge of 1 negative, which means when I combine a group 1 metal with a halogen, the formula is always going to come out metal symbol, halogen symbol, because the ones will cross down. Okay, there's not going to be any reducing. So let's take a look at combining a group 1 metal with a halogen. Okay, and then we'll look at the group 2 metals. But go on, and while I have this up here, all group 2 metals have a 2 positive charge, which means when I combine a group 2 metal with a halogen, I'm always going to get a formula of the metal and then the halogen with a subscript of 2, because the positive 2 crosses down to become that subscript. So let's take a look at a couple of examples for this. Okay. The other thing that I want to remind you of is that the halogens, fluorine, chlorine, bromine, iodine, those are all diatomic. So when we write out any reaction that contains fluorine, it's always F2. So my metal reacts with fluorine, F2. If I'm reacting it with chlorine, that's going to be with Cl2. If I react it with bromine, that's going to be with Br2. And if I react it with iodine, that is I2. Okay? So let's just kind of take a look real quick at how this works. If I take a group 1 metal like sodium, just like we did when we combined metal with oxygen with fluorine, we're again going to think about what would be the charge of sodium within a compound. And it's that 1 positive. Fluorine, as I mentioned just a moment ago, because it's a column 17, that is going to be a -1 charge. And when I cross down, as I talked about whenever I introduced this, my formula is going to be NaF. Right? And one of the things that I haven't mentioned so far, but it becomes very apparent in these, is that I'm not balancing the equations right now. Okay, so that's why I start with 2 fluorines and only end with 1. But if I'm going to balance these, this is what's really nice about group 1 metals combined with halogens. These always balance out as 2, 1, 2 if you've got it written as metal plus halogen yields your product. That way, you'll notice now I start with 2 fluorines, I end with 2 fluorines, begin with 2 sodiums, end with 2 fluorines. And if that balancing didn't make sense, again, go back and watch the videos that I've made on balancing equations. Okay, so getting rid of that real quick. Same type of thing if I combine it with chlorine. Okay, if I take, I'm going to go on and use this Mg magnesium, and sorry, that would be a group 2. Sorry, my other group 1 metal, we'll say potassium. Okay, I almost jumped ahead to group 2 metals. Sorry. So potassium, again, as an ion would be K positive. That Cl would be that 1 negative. And when I cross down, I'm going to get KCl. Right? So this is with group 1 metals. All right. You pretty much just, as always, look at what those charges are, which are going to be 1s, cross them down. So really it's the symbol of the metal plus the symbol of the non-metal. You just drop that 2 off of that non-metal halogen. If I am now dealing with a group 2 halogen, or sorry, a group 2 metal combined with a halogen, so now I can look at magnesium reacting with something like fluorine. Again, as we've been doing, I'm going to think about the fact that magnesium has a 2 positive charge. Fluorine as a halogen in column 17 has a 1 negative charge. And we're going to cross down those charges, and I get MgF2. And what's really nice about when you have a group 2 metal combining with the halogen, these equations come out already balanced with all 1s. Okay? So let's take a look at another group 2 reacting with the halogen. I'm going to go on and use bromine since I haven't already. And let's look at calcium. So calcium reacts with bromine. And as always, feel like a broken record, we're going to look at the charge that calcium would have as an ion. Bromine as a halogen, column 17, would be a -1 charge. Cross over those charges, and I get Ca1Br2, and I get my calcium bromide. And again, the equation's already balanced. So that's combining group 1 metals with a halogen and group 2 metals with a halogen. Again, what we're doing, as always, is looking at what charges they would have within a compound, writing out the symbols with those charges and crossing down those charges. Okay? So now we get into something a little more complex. Okay? The first of those being metal oxides reacting with water. And when you combine a metal oxide, so something like magnesium oxide that we produced just a little bit ago, and we put it in water, we're always going to end up getting a metallic hydroxide. So let's just take a look at that. Magnesium oxide plus water yields. Now, to me, the easiest way to work these is, instead of thinking about water as H2O, instead think about it in terms of HOH. And now there needs to be some memorization on this, or just recall that when I see magnesium oxide or a metal oxide reacting with water, I'm going to end up getting that metal combined with the hydride polyatomic ion, or the hydroxide, not the hydride, sorry. So what I look at is that metal as Mg, and again, with a charge on it, and I'm reacting with the OH, the hydroxide. Because again, I'm going to produce a metal hydroxide. And now you'll notice we're back to what we've been doing of crossing down those charges, and I get Mg, unwritten 1, OH, and because the subscript that I've crossed down is greater than 1, that hydroxide has to go into parentheses. That way I know I've got 2 hydroxide groups. So this is the way that I look at, so you can see that OH group as a nice little reminder of what's going to be reacting with your metal. So let's take a look at another one. Right. Let's take our aluminum oxide that we got just a little bit ago, Al2O3, and react it with water. Again, I'm going to always think about water in terms of HOH. It's two hydrogens, one oxygen. And again, as soon as I think and I see that OH and I've got a metal oxide, I'm interested in the metal component. So in this case, aluminum. Look up the charge to be a 3 positive. And then that hydroxide, OH negative, cross down those charges. Al1, OH3. So Al unwritten 1, OH 3. And again, OH goes in parentheses because the subscript that I've crossed down is greater than 1. So that is a metal oxide combining with water. The last type that we're going to be looking at is the non-metal oxides reacting with water, and these produce what's called oxyacids. And you'll see these in textbooks a couple of different ways. I'm just going to show you one example because, in all honesty, non-metal oxides reacting with water are not the best examples of synthesis reactions that you get, right? And I'll kind of illustrate that to you as well. But in this, let's take something like So2 reacts with water. So my non-metal oxide. And what textbooks are going to tell you to do is, because this produces an oxyacid, we know that our first component has to be hydrogen. H has a 1 positive. As far as our negative component, though, what they do is they talk about this oxygen coming over, and I get SO3 and then a charge on it. And to look up the SO3 on the polyatomic ion sheet, find that my sulfite carries actually a -2 negative charge to it, and then cross down like we've been doing, and you get H2SO3. Okay? So this would be sulfuric acid. So this is how they do it. Again, they move the oxygen over, you find the polyatomic ion, look up the charge on that polyatomic ion, and then combine it with hydrogen. Okay? So another little example of this would be if I take carbon dioxide and react it with water. What they would tell me to do is bring that oxygen over, call this CO3, look up that charge on the periodic table, find it as a 2 negative, and because it's going to produce an oxyacid, the fact that it's an acid means the first component is going to be hydrogen, and then we cross down those charges again, and I get H2CO3, or carbonic acid. Okay, so that's the way they do this. But the reason why I tell you that these don't always fit this format is because if I take something like NO2, nitrogen dioxide, and without going too in depth in this, we actually produce HCO2 and, well, not CO2, I might still on the last one, HNO2, and we produce HNO3. This does not fit a synthesis process. Okay, so anytime you have a non-metal oxide with water, sometimes you actually don't get a true synthesis reaction. So be careful when you see non-metal oxides reacting with water. Okay, so that right there are the different types of synthesis reactions that you can see within chemistry. Again, reacting with oxygen, reacting with sulfur, group 1 or group 2 metals with your halogens, your metal oxides reacting with water, or non-metal oxides reacting with water. Okay, so if you have any questions or comments, please leave them for me. If you have ideas for future videos, I'd love to hear them. Thanks for joining me, and as always, take care.